All right, now we're going to talk about a couple models of population growth, and we'll get into what kind of autonomous differential equations we can have. So the very simplest model of population growth is dp by dt, where p is population. The population changes by some constant times the current population. We call this the reproductive constant. That's for every person, how many people do they reproduce? And for species such as humans, where we take 2 people to reproduce, we might divide that by 2. Okay, and that's an easy differential equation to solve. We've solved that many times. Let's just quickly do it. I don't have any of these solutions memorized, but it's very quick. Natural log of absolute value of p. P does not equal 0, by the way, because we divided both sides by it. This is RT plus a constant, so that means absolute value of p is e to the RT plus c, which is k, e to the RT, where k is greater than 0, and then to get rid of this absolute value and also incorporate this p back in, p is k, e to the RT, where k is any real number. Okay, so the solution is exponential, so we can sketch the graph to look kind of like that. Exponential where the power is positive. That's important. R is greater than 0. If it equals 0, then the population dies out. You can't actually, if it were less than 0, that would be not reproducing and maybe killing people. We're not doing that. We're doing normal population growth. Okay, but population doesn't actually work this way. If we let people continue to reproduce as much as they wanted, like let's say on average every family was having 3 kids, then we would have a reproductive constant of 1.5 because 2 people produce 3 people, so each person produces 1.5 people. Then we would have some sort of exponential growth. But maybe at some point the people start looking around and there's too many people around. The population is too high, and they're like, whoa, maybe we shouldn't have 3 kids. Maybe they think of it consciously, but also biologically this will happen. So it happens in animal populations as well. So what we actually get is we get a carrying capacity, and that depends on the environment. So if you live in a country that's overpopulated, people tend to have fewer children, whether by law or just by some sort of biological thing. So here's P and T. Instead of this exponential growth, we're going to stop at this carrying capacity K. We know that the environment cannot sustain this. And so everything, we're going to look exponential, but then as we approach the carrying capacity, we're going to mellow out, and we're never going to go over it. And then if for some reason we started over it, people are just going to kind of die off, and we'll approach it over here. So this is what population actually tends to look at. So what is this? This looks a lot like the autonomous equation of the polynomial that we graphed before. We've got negative slope up here, we've got positive slope down here, and we don't know, it doesn't really matter what's going on down here. We can't actually have negative population. And then we have equilibriums at 0. If we start off with 0 people, we can't make people, and equilibrium at k. So this is dp by dt equals some polynomial with roots 0 and k, and then as p gets really big, it looks like the slope is getting steeper, but still negative, right? So dp by dt is negative infinity. Okay, so we need the leading term, the leading coefficient of the polynomial to be negative. So like if we just had any coefficient alpha, we guarantee roots of 0 with a p and k with a p minus k. But since this is negative, alpha is negative. So alpha is negative. Or we could write it, we'll switch this to k minus p, where gamma is positive. This takes care of the graph being negative as we get bigger. Okay, so differential equation looks kind of like this. And then in books the formula for this is what we call logistic growth. And all we're doing here is we're changing the constants around. So basically this is the formula, but we're going to change the constants around. So we're going to write dp by dt is r times 1 minus p over k. Notice that 1 minus p over k still gives me a root of k. It's just k minus p divided through by k. So we're going to subsume the k into the gamma and write r instead, times p. And what this does is if you expand it, we don't really care about this, but there's an rp term minus, this is now rp squared over k. But that looks a little bit more like our original population growth. So that's what this formulation of it does. So that's the general equation for logistic growth. And note this is autonomous, which also means it's separable. May need partial fractions to actually integrate this. Let's actually do that. So this is actually, we made it a little bit uglier algebraically, right? This is not going to be the best format to integrate, but we can do it. So let's see. Let's separate it. We got dp over r times 1 minus p over k times p. Oh, actually, let's leave the r on the other side. Equals r dt. And now we can integrate both sides. And then we need partial fractions. So the left side is going to be in the format a over p plus b over 1 minus p over k. This is dp. And the right side we can actually integrate directly. This is rt plus a constant. Okay, let's figure out what a and b are. So if we find a common denominator, then the numerator we get, a times 1 minus p over k plus bp, and that has to be compared to this fraction, which is 1 over the common denominator, so that has to equal 1. So if you expanded that out, the constant term on the left would just be a, so a equals 1, and then the p coefficient on the left would be b minus a over k. And the p coefficient on the right is 0, so that's 0. Okay? So then if we sub 1 into 2, we get b minus 1 over k is 0, which means b equals 1 over k. Okay, so then we can actually integrate whatever these are now. A is 1, so integral of 1 over p plus, this is 1 over k over 1 minus p over k dp. Right-hand side is still rt plus c. Now we integrate. This is natural log of absolute value of p plus, or maybe minus, right? So the derivative of 1 minus p over k with respect to p is negative 1 over k. So you can do a u sub or think of it all at once as a chain rule. You end up getting natural log of 1 minus p over k with a negative sign. And then the constants we'll just assume is subsumed into the right side. Okay, and remember our log properties, log of something minus log of something else is the log of the quotient. So p over 1 minus p over k, technically still an absolute value, is rt plus c. So that means absolute value of p over 1 minus p over k is e to the rt plus c. And then we've already used k, so let's get some other constant here. This is like c1 e to the rt, and then where c1 is greater than 0, because c1 is e to the c. But then we have this absolute value. We probably had some 0 stuff going on. We probably said p could not be 0 at the beginning when we divided by it. So we can get rid of all of that. And we say p over 1 minus p over k is c we'll still call it C1, e to the RT, where C1 is now any real number. Okay, now we need to get P by itself. We want P as a function of T, right? So we gotta do more algebra. Let's leave this here. We're gonna multiply both sides by the denominator, so P is, and we'll expand this out as we go along. It's okay to do multiple steps. That way you write fewer lines. You actually save yourself time on quizzes and tests. There's not going to be a time crunch on quizzes in this class because it's not fair enough to, it's too hard to guarantee that everyone gets the same amount of time. If someone says they have technical difficulties, I'm going to give them a couple extra minutes probably, and then who knows what's going to happen. So not a problem in this class, but usually people talk about running out of time. Okay, we're going to common factor out a P. This is 1 plus 1 over K, C1 e to the RT equals C1 e to the RT. Divide both sides by this. Looks a little bit ugly. We're going to make it prettier in a second. C1 e to the RT over 1 plus 1 over K, C1 e to the RT. And we notice that there's a common factor of C1 e to the RT in a lot of places. So like, let's actually divide top and bottom by C1 e to the RT. So this is going to be 1 over, this is 1 over C1, we're going to call C2, e to the negative RT plus 1 over K. And this is very close to the format of the solution that we want. We don't want this 1 over K, so we're actually going to multiply top and bottom by K as well. So this is K over, this will be a 1 now, plus, and then K times C2 I'm going to call C3, e to the negative RT. Okay. That is the format we keep the function of the population in. So we write P of T equals this. Why do we write it like this? This is so that we can look at a limit. So as t goes to infinity, then what happens? Well, this part goes to 0, so the denominator goes to 1. So P of T actually goes to K over 1, which is K. So that's cool. K is the carrying capacity. So this actually tells us what we said at the beginning, is if we're either above or below the carrying capacity, the population is going to tend to the carrying capacity.